Is Pluto young? Well, first we probably need some background information. Some of the expectations that there were for Pluto. Well, number one, Pluto is cold. How cold? Well, most of the time, Pluto is the furthest planet away from the Sun. Now, there's actually a small percentage of it, it's about 250 years that it makes a circuit, that it's actually closer to the Sun than Neptune. But most of the time, and that includes right now, it's out further away. The sources are listed on in the slides. It's also odd in that almost all of the other planets orbit in a flat plane, but Pluto, in contrast, has an orbit that is inclined about some 20 degrees or so from the plane that all the other planets live in, including our Earth. And for a better idea of the scale that we're talking about, there's a website that I recommend for you because it puts the moon at 1 pixel and then draws what the rest of the solar system is like exactly to scale, and it is amazing. So most of the time, including right now, the Pluto is the furthest planet away from the Sun, which means that, in general, it's the coldest. The temperature of Pluto is estimated to be at 387 to 369 degrees Fahrenheit, or about 233 to 223 degrees centigrade, below zero. In absolute Kelvin, that's 30 to 40 Kelvin. That is cold. You want to know how cold that is? Well, the coldest temperature measured on Earth was about 127 or maybe 128 degrees Fahrenheit at Vostok, Antarctica. That's cold enough. That's minus 88 degrees centigrade. And to give you some idea of how cold that is, carbon dioxide, dry ice, it freezes at normal pressure at about minus 78.5. So you could take carbon dioxide and take it up to down to or out to the South Pole and sit it there during the winter, and it would actually congeal into a lump. That's how cold the South Pole is. Well, but see, that's minus 78. Liquid nitrogen boils at a minus 196, or about 77 Kelvin, and liquid nitrogen freezes at about 63 Kelvin at normal pressure. And so Pluto is 40 to 30 Kelvin. It is so cold that nitrogen would be in a frozen state on Pluto. And in fact, it is. That's cold. Well, that means nothing moves. So it was initially believed that Pluto would be heavily cratered, and for good reason. Most moons are heavily cratered. The only reasons in standard geology for craters not to show would be geologic activity, that is resurfacing, or erosion, which would require an atmosphere. And Pluto has an atmosphere, but it's like 1/1000th of what it is on Earth. Very, very thin. And if you look at objects that don't have an atmosphere and don't have a lot of resurfacing, such as Earth's moon, you can see that they're covered with craters. Big craters, little craters. And in fact, if you get up closer, you can see there are craters everywhere except for these dark spots, which are thought to be melted areas. And here's a little close-up, and you can see craters and craters and craters and more craters. And the melted spots seem to be mostly absent of craters. There's a few of them. But the rest of the moon is just packed with craters. Now, if you think the front side of the moon is tough, take a look at the back side. I mean, it's one solid mass of craters. Get a little closer and you get a better idea. Just massive craters everywhere. Just amazing. And craters within craters. And craters overlapping other craters, where this one formed and this one kind of came through and moved it out. Well, now that happens on Earth too, rarely. But most of the time when you have a crater like this, it gets eroded. So this crater in Arizona is one of the few that you can just look at and see that you've got a meteor crater. By the way, there was a long dispute over this crater. People originally claimed that this was due to some kind of volcanic activity, an explosion, steam explosion, something. And they finally decided that no, indeed, it was due to an asteroid that hit. Well, even planets get that way. Look at Mercury. And, you can't, there's a lot of other things there, but if you get close, you can see that there's craters upon craters upon craters. Mercury is just covered with craters. Mars has an atmosphere, so it burns up a lot of the stuff that comes at it, just like Earth does. And so you don't see quite so many craters on Mars, although you do, but Mars's moons obviously have craters on them, and these are little tiny objects that don't have enough gravity to pull in too many objects. But you can see this one really took it on the nose. Phobos and Deimos. Well, now Jupiter's moons are a little bit different. Io, the closest moon into Jupiter, really has very little cratering at all. And that's probably because it keeps getting resurfaced. There's actually volcanic type activity that's coming out in Io. Europa also has that same kind of refreshing activity, and therefore you don't see too many craters. You do see one here, but that's about it. A little closer up to Europa. Ganymede has quite a few craters, and Callisto is covered with them, somewhat similar to our moon, especially the backside. Now, I will hasten to add that these pictures are not to scale. Ganymede is the largest, Callisto is the next largest, Europa is the smallest, and Io is an in-between size. Saturn's moons, Titan, which is by far the largest moon, has an atmosphere, and you can't really see too much, and there doesn't appear to be that kind of full surface cratering on Titan. But some of the other moons, Tethys, which is, you can see it took a nice hit here, but also it's pockmarked with craters, and the same way with Rhea, and Dione, and Epimetheus, and Iapis, although this has some smoothing in some areas, but still you can see there's cratering all over it. Phoebe, Janus, and my favorite, Mimas, otherwise known as the Death Star. Enceladus, one of the other large moons, has resurfacing in part of it, although you can see that there are some of the surface that's pretty old and has craters on it. So unless you have some way of resurfacing, all of the moons so far are pretty well cratered, and Mercury is cratered as well. Miranda has an interesting appearance in that it looks like it's kind of been put together by a committee here. but at least some of the surface looks old and cratered. And there are a few craters even in the newer stuff, whatever that is. Ariel has apparently been partly resurfaced, but again, you have craters in it. We're going outward from the planet, and as we go out further, we have Umbriel with craters, Titania with craters. Unfortunately, I don't have a better shot at some of this. And Oberon with craters. So it looks like everything in Uranus has craters. Neptune's moon, Triton, appears to have some resurfacing. It is hypothesized that it had some kind of contact with something else that melted a part of its surface and then smoothed everything out, although you'll notice that there are some parts of it that look like they've pretty well beat up, although it's hard to pick out too many craters from it. And Proteus, the other decent-sized moon of Neptune, although it's not very big, it's small enough that it hasn't rounded itself out, also looks pretty beat up. And you can imagine that there's some kind of cratering going on with Proteus as well. So, just to give you a bit of the scale that we're talking about, there's Earth's moon, and it's a little bigger than Europa and a little smaller than Jupiter, than Io, and Ganymede and Callisto, the first and third, and Titan, the second largest moons, and Triton, the largest moon of Neptune, and the moons of Uranus are pretty small. Charon is comparable to some of those. Or perhaps it's easier if we line them up this way, where here's Earth and Venus and Mars. And interestingly, the next one should be Mercury, but isn't. It's Ganymede and then Titan from Saturn's moons, and then Mercury, and Callisto and Io. Is Mercury not really a planet? Well, it's cleared out everything around it, I guess. Then the Io, the moon, our moon, Europa, and then Triton, Neptune's moon, largest moon, and then we get to Pluto. You can see Pluto is quite a ways down the line there, but it's all by itself. And there's Charon, which is probably the largest moon for a planet anywhere, with the various, and by the way, there's Mimas, the Death Star is right there. Or maybe it's easier to see it this way. Here's the sun. That's Earth size, Jupiter, Saturn, Uranus, and Neptune. And then if you look at the other planets, Earth, Venus, Mars, Ganymede, Titan, Mercury, and here's our moon between Io and Europa, and then Triton, and then Pluto. And then Eris, which is one of the reasons why we're kind of arguing that maybe Pluto isn't a planet. Either that or we're going to have to start naming 9th, 10th, 11th, 12th, 13th, 14th, 15th planets. Where do we stop? There's Charon, Pluto's moon. And interestingly enough, the largest asteroid is quite a ways down the list as well. Ceres belongs in this general area. So it is perhaps not surprising that Pluto was expected to have craters like any other object in its area. And I refer you to an article that came out before we got to Pluto. And you see here's Pluto and Charon, and that's the best photo we have. So you can kind of imagine it to be anything you want. Well, this is their imagination, with lots of craters around everywhere. maybe a few Maria or something like that. And this is from the International Astronomical Union, whose business it is to name things officially on planets. And you will notice that their website, which I'll give, had a drawing of Pluto and Charon. I'll give it to you with a little more detail there. Charon is quite a ways in the background, and so therefore is much smaller, although in reality it probably, if they were side by side, would be something of that order. But you can see pock marks everywhere, big craters, little craters, everything. That's kind of what you would expect. Well, this is what you get. When we actually flew by, yes, maybe there's a crater here. One there, one there. But we have whole areas where there are no craters at all. And in fact, even some areas where it's rough, there are no craters. There are actually what I guess you would call mountains instead, which led to an article by Dr. Danny Faulkner called Pluto's Surface is Young. And we're going to go over that article and then kind of critique it a little bit. The article can be found in the Answers in Genesis website. It starts out on Wednesday, July 15, 2015. NASA released the first close images of Pluto recently taken by the New Horizons space probe. What the photos revealed was a shock to conventional uniformitarian scientists who believe in a 4.5 billion-year-old solar system. Over the past half-century, planetary scientists have become accustomed to finding many impact craters on the surfaces of bodies in the solar system. We've seen some of those. However, from the preliminary photos of Pluto's surface, these scientists have found far fewer craters than they expected. Earlier wide-field views of half of Pluto's surface seemed to indicate a few craters, but the first close-up region examined appeared to have no craters. And those give you links, and I'll give you the links. And then we'll look at, one of the links to the picture we just looked at, which is kind of the classical Pluto photo now. Notice the heart in the middle of it. And the second link showed some of the mountains, which are hypothesized to be made of water ice. Some of the mountains are 11,000 feet or 3,300 meters. You want to get an idea how high that is? Look out here at San Gorgonio sometime. That's about 11,000 feet. So these mountains are in that range. And you'll notice that smooth, uncratered terrain, this is not from our article, this is from the article which it referenced, suggests the region has been geologically active in the last 100 million years. And then they showed Charon, which has a canyon which may be 4 to 6 miles deep. That's Grand Canyon size. Series of troughs and cliffs for no apparent reason. No, the smooth region, well, it's smooth, but it still has a few craters, but kind of like the Maria on the moon. This region, by the way, has been called Mordor. Those of you who are Tolkien fans will appreciate that. Most scientists think that the solar system formed approximately 4.5 billion years, returning to our article. So they interpret craters in terms of their accumulation during that time. I'm not reading the entire article. I'm skipping little tiny pieces of it. And where I skip, you can see. Supposedly, many of the impacts were from leftover material that did not form into planets. If true, then the rate at which craters formed was much greater in the solar system, early solar system, than it is today. Some surfaces, such as Earth's and Jupiter's satellite Io, have relatively few craters. Planetary scientists explain this by geological processes that remove or cover craters. On Earth, the main geological processes responsible for this are believed to be the sedimentation and igneous activity accompanying plate tectonics and weathering and erosion. On Io, the principal mechanism of crater removal is volcanism. Io has many active volcanoes that change the surface regularly. Some surfaces of solar system bodies, such as Earth's moon, have regions of high crater density, which we saw, and regions of low crater density, the Maria. This is explained by volcanism that affects parts of them, such as our moon, and not others. Planetary scientists use crater density to judge the relative ages of various surfaces and regions. The lunar Maria appear to be volcanic plains and have far fewer craters on them than on the heavily cratered lunar highlands. Presumably, the volcanism and related processes that formed the lunar Maria covered over many of the craters originally there. Hence, the Maria are younger than the lunar highlands. By the way, the Maria were originally thought to be seas, and that's why they're called Maria, because mar means sea in Latin. Similarly, the craterless surface of Io is very young, as evidenced by ongoing volcanism that we have witnessed occurring on its surface. Europa, another large satellite of Jupiter, only has a few craters, suggesting that its surface has been reworked, though not as recently as Io's. The two other large satellites of Jupiter, Ganymede and Callisto, have increasing crater densities, suggesting still older surfaces, but surfaces that have been reworked to some degree. Although Callisto looks pretty cold to me. The densities of craters on the surfaces of these four large satellites of Jupiter increase with distance from the planet, as do the inferred ages of their surfaces. This disparity is explained in terms of tidal flexing of Jupiter's strong gravity that heats those satellites' interiors to permit volcanic activity. The tidal heating decreases with distance from Jupiter, which kind of makes sense. With the exception of Io, every surface on solar system bodies that we've examined, planets, their satellites, asteroids, even comets, appear to have impact craters, suggesting most planetary scientists that they all have a great age. This is why the lack of craters on Pluto is such a shock, or the relative lack of craters. Being far from the sun, Pluto ought to be very cold, and hence not to have experienced recent volcanism. Any primordial heat would have long since dissipated if the solar system were 4.5 billion years old. The density of Pluto is very small, 2.0 grams per cc, which is about twice that of water, which is consistent with a roughly half and half rock and ice composition. This density will not allow for long-lived radioactive elements. We're thinking uranium, potassium, which allegedly are the source of Earth's internal heat to provide for the continuous geological activity during Earth's supposed 4.5 billion year history. Nor is Pluto near any large body that could raise the tides within Pluto to heat its interior and thus drive surface geological activity, as supposedly is the case with Jupiter's large satellites. Hence, there ought not to be any significant geological activity sufficient to remove craters on Pluto's surface.
Paul, can you explain, go back, about the radioactive elements? It seems to be in the context of the density, but it seems like you don't need very much of the heavy elements to create heat.
Well, it's not a matter of just heat, it's a matter of how much heat. And that's the question. Is there enough heat to do the job? And the feeling is that there's, on Earth, there's a high enough concentration of uranium to actually make a difference.
So how do we know how much uranium there might be on Pluto?
Well, here's the problem. Uranium has a density of well over 10. It's, I looked it up recently. It's something, I think it's over 13 grams per cc. So if you have a lot of uranium, then the rest of Pluto would have to be made of ice only, or of nitrogen, or some very light material. Because otherwise its average density couldn't be 2.0.
You wouldn't need most of the rock to be uranium to produce enough heat, is that right?
Well, you'd have to have a substantial portion of it.
But you don't know that. You haven't gone through the calculations to find out exactly what the change in temperature would be if you had a certain percentage of uranium in that portion of the rock that is there. So you're comparing it to the Earth, you're trying to get molten lava. All you're trying to do is get some ice gas reaction to occur on Pluto to drive the process, a volcanism process. It doesn't take much to do that.
It wouldn't take as much as it would for Earth.
What's that?
It wouldn't take as much as it would for Earth because
Very
it's,
little.
yeah.
And Danny Faulkner has no indication that he's gone through any kind of calculation. He's just speculating.
Well, we're gonna talk about some of what Danny Faulkner has to say in just a little bit.
How in the world do they get the density?
Pardon me?
How do they estimate the density of the planet that far away? What do you do to estimate something?
I'm sorry. How do they estimate?
How do you estimate the density of a planet like that so far away?
You figure the strength of its gravitational field, and you figure its size by visual inspection.
You only need mass and volume, and also
Yeah.
there's a lot of calculated mass, and then you can use this by observing the passage of the moon. Its moon in front of the planet, you can determine its size, and they were able to get it. They knew it ahead of time, I think, 2 kilometers.
It was a little larger than they expected,
Yeah,
though.
it was a little larger than they expected. But they knew ahead of time, within 2 kilometers, what its size would be and thus its density. They know the mass very well because of its orbit around the sun. Kepler's laws.
So even, I mean, the density was not a huge surprise. It's a little bit lighter than they expected. But not,
it
but
was a
not
little
much.
lighter than expected. Yeah, there is a
But
little
not very
larger than
much.
expected.
I mean,
yeah.
Probably went from 2.03 to 2.01 or something like that. It's a very, very small difference there. And you're right. If I were writing that article, I would want to be saying how much uranium it would take, how much potassium it would take. Actually, potassium heats more than uranium because it has a higher rate of radioactivity, a smaller half-life.
Which under standard thinking would mean that it would have expended all of its energy in the distant past and therefore would resurface it recently.
It would have expended more of its energy, significantly more. The half-life is 1.25 billion years, if my memory serves correctly, which means that we're at 4.5. We're down a little over 3 half-lives. So we have maybe a tenth of the activity that it would have started out with. And it would be worthwhile going through the calculations. How much potassium would you expect in the standard rock? And would it be enough to give the heat you wanted? And I agree. I think that this is a defect of this particular article. Compounding this problem for a 4.5 billion year age for the solar system is the fact that Pluto is located in a particular crowded part of the solar system, which means that therefore Pluto ought to be undergoing impacts today at a higher rate than most other objects in most other portions of the solar system. Except for probably the asteroid belt. Planetary scientists who are committed to belief in a 4.5 billion year old solar system are at a complete loss to explain the lack of craters on Pluto. But the situation is even bleaker for them. Pluto has a tenuous nitrogen atmosphere. This nitrogen is leaking away from Pluto's atmosphere, so it must be continually replaced. One can claim that the unknown mechanism driving the geological activity on Pluto also is bringing nitrogen from Pluto's interior to the surface where it is outgassed, but Pluto is a small body and it has only a finite amount of nitrogen. It is possible that after billions of years, all of its nitrogen should have been depleted long ago. Now, I note that there are no discussions of amounts, and we're going to quantify that argument in just a little bit. There are mountains on Pluto's surface that are 11,000 feet, 3,300 meters high. The rock or ice composition of Pluto probably could support such a tall structure with Pluto's modest gravity if Pluto's interior is very cold. However, if Pluto is as warm and geologically active as inferred, then the rock ice structure of Pluto could not support such mountains for long because their bases would sink. Therefore, these mountains must be very young. All of these considerations demonstrate that Pluto is a young object, far younger than the 4.5 billion years that most scientists assume. At least that's what Faulkner is claiming. Charon, Pluto's largest satellite, offered stunning news too. Charon appears to have a few craters, but far fewer than expected. Its surface also is gashed by a large chasm, suggesting recent or ongoing geological activity. This too was unexpected in a solar system that is 4.5 billion years old. We may yet find a few craters on Pluto's surface, but those would be inconsequential to the conclusions that we can draw. It is very clear that Pluto is young, far younger than the billions of years generally assumed. While this is unexpected and hence unexplainable for evolutionists, this is something that we might expect if the universe is only thousands of years old, as the Bible indicates. The preliminary results from the New Horizons space probe are good news indeed for the recent creation model. That's what Danny Faulkner wrote. Now, I'm going to give you my take, and then I'm going to turn you loose on it. There have been no reactions to these claims, this very recent material, and we may or may not ever see those reactions for various reasons. One, people not paying attention to Faulkner. Two, people not wanting to dignify Faulkner's article with a response. I have a very small dog in this hunt, but not a very big one, and one that I could easily let go. I slightly favor a short age for the solar system, not the universe. I could easily live with Earth's surface that has been reworked with the rest of the solar system old, as I used to. So that's not an insurmountable problem, and I think it's more important for us to be honest than it is for us to support our theories. The argument that the surface of Pluto is young, I think, is reasonable. Here are some other data, and I'm going to get them from theguardian.com, which is supposed to be reporting news. And there's Charon, and you can see on Charon clearly craters, but not as many of them as we see on most other surfaces. And also clearly more craters than you have on Pluto itself, which suggests that Pluto resurfaced after Charon did. To quote the article, researcher Fran Bagendi said that based on models and a pretty good guess, she expects Pluto's atmosphere is escaping at the rate of 500 tons per hour, hundreds of times faster than the escape of Mars' atmosphere. 500 tons an hour, that sounds terrible. Well, let's put some numbers to it. That's assuming that those are metric tons of 2,200 pounds, which they probably are now that Great Britain is on the metric system. So we're looking at 500,000 kilograms per hour. 24 hours a day, 365 and not quite a quarter days per year. 4.5 times 10 to the 9th years equals 2 times 10 to the 19th kilograms. That sounds like a lot of material. Now, before we go too far, I'm going to point out it might not be quite that much, because the atmosphere on Pluto is collapsing. And the instinctive reason that I would give for it collapsing is Pluto is starting to get out further from the sun, and so the supply to the atmosphere is kind of being cut off and the atmosphere is escaping. And perhaps it doesn't escape quite that much once Pluto goes out to the very end of its orbit, although maybe it escapes more when it's closer to the sun. So that maybe it's really 1 times 10 to the 19th kilograms. But even if you allow it for 2, that compares with Pluto as 0.15% of Pluto's weight. Well, that's not very much. All you've got to do is stock Pluto with a little extra nitrogen to handle the 4.5 billion years. So I'm afraid that that argument really doesn't hold water. Now, Faulkner's not the only one to make kind of dumb mistakes. Data downloaded in the following 24 hours provided the first close-up image of the surface, and it revealed an ice mountain range that rivals the Rockies in height, but hundreds of millions of years younger. Ariel, how old are the Rockies now?
You mean what I think? How old?
Well, I mean, what is the standard geologic age?
Oh, man.
Isn't it like 100 million or maybe 150, 70 million? How can you be hundreds of millions of years younger than the Rockies? Anyway, just, other people make mistakes too. Stern said that data should soon be able to confirm that the mountains are made of water ice, whether nitrogen snows on Pluto is suspected, and that the world has water in great abundance. That's what they think, and they might be right. So, there are a few other people whose quantitative abilities are limited, shall we say. In another article that actually referenced that article, Stuart Clark in 2015 in The Guardian, and again, this is not, official, but this is somebody who got this from officials, and as you'll see, I think the photos back him up. Number 7, 10 things we know about Pluto. Pluto's surface looks like boiling milk. The smooth plains of Tomball Regio, that's that heart-shaped region, particularly the part on the left, have been called Sputnik Planum after the first Russian satellite launched in 1957. Much of these plains are separated into blocks, each about 12 miles wide. They resemble the pattern of convection cells seen in steadily boiling milk. Perhaps they are where heat escaped from the interior of Pluto and temporarily melted the surface before freezing over again, immortalizing the pattern. I'm going to take a look. There we are. And you can see areas that are kind of, cell-like. And it looks like they were, coming up from the inside and then going down in the cracks in between, and somehow got frozen in the middle of that. And if you'll look very carefully, you will see that there are none of the standard craters in there. So this looks like pretty recent. How recent? 100,000, 100 million, 4,000, who knows? Now, in my opinion, the disappearing nitrogen is not a significant problem for an old Pluto. And I'm going to agree that there's a possibility that the heat source is not a big problem. I do think that Pluto has been resurfaced recently. And I do think that there's a problem with keeping the mountains going while you're heating the interior enough to where it boils over in areas. So I think there's a problem with keeping those mountains for a long time. Does this destroy an old Pluto? Not really. One can try to make a model where Pluto was an escaped satellite of Neptune, and one can say that it happened fairly recently, And in the middle of that escape, when some other object came to it, or perhaps Pluto had a close encounter with Neptune and got flung into a different orbit, in the process of that, Pluto got heated much the same way Io is heated. And therefore Pluto sort of boiled over like that milk, resurfaced completely, and that's why you don't see that many craters. Now, what I think will not work is the idea that Pluto's been in that same orbit for 4.5 billion years without any change. I think something has happened to Pluto recently. It's just we're not able to say for sure that it was created, and I don't think that we should expect to. And therefore, I think that this is an argument that it's strong for arguing that the standard model doesn't work. It's not very strong for arguing that that Pluto is absolutely young. And I think that's something to keep in mind. It's very much like the rings of Saturn that are good arguments that something happened recently in Saturn to put all this debris there, because over billions of years it should have collapsed. But it doesn't argue that Saturn itself isn't 4.5 billion years or whatever old. And I think we have to be very careful not to extend our arguments past the points that they can make. But that's my opinion, and now it's your turn.
What is your argument for that last point? Why you just say it's not 4.5? I just want to know what your argument was for it.
Well, why it would be 4.5, or why it isn't 4.5?
Why it isn't?
Why it isn't?
Yeah.
Well, like I say, I think the surface, or for example, the rings themselves, probably don't make a lot of sense to have been there for billions of years, or they would have coalesced, collapsed. I don't think they're stable for that period of time. But on the other hand, that doesn't mean that a planet couldn't have gotten in there, gotten torn up, and shredded into particles that wound up with rings for a while. And this kind of thing, you can make arguments for it. I think the problem that you have is that they don't prove what these people want to prove. Yeah. And I'm sympathetic with their goals, but I think you have to be careful about overextending your argument.
I find one point particularly weak in the argument. It seemed to me when you were going through the last end there of Faulkner's arguments, Pluto is young, therefore the whole solar system is young.
Well, that's right. I mean, Pluto could be a new planet that just kicked off Neptune, let's say, 2 million years ago, which for the solar system is extremely young.
When you've got so many other craters on the other moons in the solar system, that argument falls apart completely.
The other question is, what causes all those craters? And here, we're going to have to back up a little bit, because if you look at what happened to Earth during the flood, assuming there was a flood, that the Arizona meteor crater isn't 48,000 years old, it's 4,000 years old. The Chilexicab disaster, the Chesapeake Bay disaster. There's one out that they think they can find traces of it between Madagascar and Africa. There's a whole bunch of craters that have been found in various places. There's one in Utah that we went on a bus and took a look at that is thought to be cratered by some people. There's another one in Texas I was just running into on the internet today that I didn't know existed before I started looking. There's a whole slew of craters There are meteorite fragments in supposedly in the Ordovician in Sweden or Norway, which implies impact during that time. And if the flood was relatively recent, 4,000, 6,000, whatever years ago, then that says that there was a whole bunch of bombardment a lot more recently than we think. And it raises the question as to whether some of these things could be not from just random stuff that's floating around in the solar system, but perhaps flying past another cloud of particles that's sitting there and smashing into them on the way through.
So you're claiming that there's large impacts during the flood?
I think that if you take a flood, you're kind of half forced into that way of looking at things.
That cratering in the solar system was flood or post-flood?
The cratering in the solar system, a good share of it could have been, because of what we see on Earth, a good share of it could have been as recently as, say, 4,000 or 5,000 years ago.
Around the solar system?
Pardon me?
See, the type of collisions that you're talking about, that we see evidence of, there'd still be a lot of debris, a lot of, 4,000 years ago, a lot of heating on these planets or moons that would still be evident if that was only 4,000 years
one of
ago.
the things that it might help to explain is how the moon got hot enough to melt. The moon's supposed to be cold by now. Nowhere near the heating point of lava.
The asteroid belt
Well,
indicates something odd. There's something very odd out there, which we're moving into speculation now. This is purely speculation. Some people feel may have been associated with inducing flood activity on the Earth.
Well, one of the things that could happen is that the asteroids are, instead of a planet that never collected, maybe they're a planet that was there and got hit head on and totally shattered, and then the pieces collected as best they could.
Well, there's different processes. There's been clearly temporal processes that have occurred on the moon because of, you can see where lava has flowed into craters that have previously existed.
Right.
You can't, there's no way you can squeeze that into 4,000 years, all that stuff. It's just physically impossible.
I'm not sure I would make that
Well,
case. Lava flows pretty fast.
Yeah, I know, but not cratering, lava flow, and then more cratering on top of that in a process that leaves a signature that's there, that in terms of the total events that are going on. We would see rings around all the planets if with bigger than Saturn if things like that had occurred just 4,000 years ago. It takes a lot of time for that kind of stuff to.
Lava flows can go awful fast, boy. I've seen them in Hawaii, boy. I'll tell you, those things really go. I need some quantitative data from you on that statement.
I'm not saying anything about the lava flow. It's a sequence of events that are clearly evidenced in the various, that there's a number of processes that have gone over time where there's been cratering, lava flows, more cratering, more lava flows, cratering, that just indicates a process that there's no way can happen in 4,000
You know what?
years. Lava flows can happen quickly. Of course they can.
I'm going to invite you to present some of that evidence and do some of the quantitative stuff behind it,
Yeah.
and come back here.
Well, that's certainly possible. Yeah.
What?
That certainly can be done.
Okay. No, I'm serious.
Yeah.
You want a month. You want, you're ready next week. You want 6 months. I give you the whatever time you like. Because I think this should be done right. I think Faulkner, in the nitrogen, clearly illustrates the mistake of not doing the math.
Well, it's just he makes the statement that it is very clear that Pluto is young. I mean, obviously, he's biased heavily
Yeah.
in his
Well, I
whole
think you can make
process.
the argument that the surface of Pluto is young, even if you don't make the
100 million
argument that
years
Pluto
is
is young.
young.
Pardon me?
For 100 million years is young for a young Earth creationist. You know, that's not young.
Well,
It's young for the universe. Very young for the universe.
Well, that's
it's
true.
it's
That's
it's
true,
much too
but-
young. It's much too young for the standard model. Let's put it that way.
Well, there's certainly some things going on Pluto, and we're just learning about new on that scale, what kind of physical processes can occur at those kind of temperatures. When you have an object like this, it's just literally mostly ice. Different kinds of ice, you know, nitrogen, carbon monoxide, carbon dioxide, water ice. All those things are there, and they all operate differently at different temperatures. You look at Enceladus on Saturn. You've got geysers going off on there. Currently, we've imaged those with.
Yeah.
And
So that's not speculation as to whether it's being
that's-
resurfaced. We can actually see it being done.
Yeah. So, but why? But we have these other objects in the solar system like Io, even Titan. There's very few craters on Titan. But we don't go around saying that the universe is young based upon the fact that those planets, those moons, show very few craters, because we see the process that's resurfacing them. It's obvious what they are. We've just discovered what this looks like. We haven't, we're so quick to jump to saying that it's young without really understanding that, trying to look into why what processes could be cause volcanism of some kind on this object. We see a nitrogen atmosphere. Nitrogen solidifies and boils and sublimates at the temperatures that Pluto's at. And so
Well, it doesn't boil at the temperature Pluto's at.
it's much closer. What you stated was a temperature that at standard temperature and pressure on the Earth. It's less. It's much less than that. And there's only about a 24-degree difference between the freezing point of nitrogen and the boiling point of nitrogen. It doesn't take much energy to get nitrogen to become really active.
But you have to get it at least to melting temperature, even under any kind of
you
pressure.
could have some kind of process going on like radioactive decay. It could have been in the past you had a liquid interior of some kind formed from nitrogen due to if it was closer to Saturn or had an orbit that was closer to the sun. And
Well, let's
time,
be careful here, and the reason I say that is because I don't want us to do a reverse Faulkner on this.
Well, no, but we do know that the orbit, like you said, and I really appreciate you recognizing that the orbit of Pluto is likely not consistent to what it is now. It could have been much different in the past. And the fact that it has retrograde motion relative to the rest of the solar system indicates that its orbit has changed significantly from when it originally formed. And so we don't know 10 million years ago or 100 million years ago what was going on with Pluto that could have generated these features that we see. It's really it really takes some bias to jump to any kind of argument at this point to say that Pluto itself is young.
No, I'm going to agree with you that from the data we have, I don't think you can make the argument that Pluto itself is young. I think what you can make the argument is Pluto, A, has been resurfaced, and B, that its mountains are going to be difficult to account for, given the heat that is apparently required to get the nitrogen to resurface.
If it doesn't take, obviously, if there's geysers on Enceladus, and it's a very small moon, and it's ejecting the gas nitrogen to escape velocity, it doesn't take much energy to create, and it's resurfacing that moon. It doesn't take much energy to get this kind of process to go. So,
No, but what I'm saying is that you're going to have to soften the inside of it significantly if a good share of it's made out of water ice, which is what is being hypothesized.
well, any viscosity requires just any kind of pressure underneath. If there's some kind of liquid layer in this planet, I mean, on Pluto, there's going to be pressure there that could easily force chunks of water ice to the surface like that. You know, and any kind, and if it's freezing out, it's creating heat. So, I mean, those are various ideas that people have talked about. So, to say that to question whether there's a lot of reason, there's good reason to go to to say that the lack of craters on there indicates that the planet is young is just
Well,
a big jump.
As I said, I'm agreeing with you.
Yeah.
I think that we have to be. We can't take that data and run with it as far as Smock wants us to run. I think that we can take that data and run as far as to say something weird has happened. But something weird has happened is a whole lot different from saying it couldn't possibly be the material be that old and have been reworked. And I think that that's one of the points I would make is that you can't take this data and argue. You can argue a little bit for a young Earth because we expected it more than they did, but that's pretty weak. That's really weak. We have a comment back. Go ahead.
I would raise a question, mostly curious here, but I don't think we can draw a parallel between Io and Pluto at all. We're dealing with ice mixed with rocks. Do we have any idea how the distribution of those rocks and that ice is? And you're going to resurface the ice, or you're going to resurface the rocks, or what are we dealing with here? This is a different animal.
We're actually resurfacing two things. One of them is solid nitrogen, probably, and the other one is solid carbon dioxide, carbon monoxide. There appears to be quite a bit of carbon monoxide in that particular part of Pluto, which means I guess you don't breathe the atmosphere, but such as it is. Let me just get a comment from way back up here, and
do you know, anybody know what the thinking is as to why the large impacts of the Maria on the moon tend to be asymmetric, or I don't know, asymmetric is the right term. It's one-sided. I mean, to me that seems unusual that you would have meteorites or asteroids coming in from what appears to me to be one direction. You'd tend to be implied that it's a flow of stuff going one direction.
I'm not sure I caught the very beginning.
Okay, the
of
Maria
the
on the
question
moon.
correctly.
They're not randomly distributed on the surface of the moon. They are on the Earth's side generally. Why would that be?
The Maria are on the other side?
Yeah, I know he's talking about the fact that the Maria that we see, the lava
That you
flows
can't see the
occurs-
Maria on the other side
Yeah,
of it.
yeah, it's full. You see lots of craters. You don't see the Maria on the backside. Well, it
That-
turns out the crust is a lot thicker on the backside, and it's likely due to the tidal interactions between the Earth and the Moon. The Moon is significant enough in size that there's a tidal force difference between the front side and the back side. That with any kind of liquid that can flow, it's going to have it's going to be affected in a differential manner between the front side and the back side.
That implies that the Maria were formed early on in the Moon's history before it had time to solidify, as I understand it has now. As far as I know, the Moon does not have a liquid core anymore.
So this is it's something that's happened in the distant past, but there's still just like there's tides on the Earth from the moon. There's going to be tides on the moon.
And that
as
implies
well.
that the Maria formed early on in Earth's history. Because if it had taken too long, the moon would have been so cold it couldn't have formed Maria.
Well, we can
So
see
at least that's the standard theory, if I understand correctly.
Well, in the formation of the moon, however, it was formed likely through some kind of collision process. I mean, that's the speculation and natural speculation on how it happened.
Right.
In that collision process, most of the moon would have become molten on its surface, and because of the gravitational force, it would have been a thinner crust formed on it could have produced a thinner crust on the Earth side as compared to the backside, and thus if there was any volcanism that generated later on for whatever reason, it would have been much easier to occur on the Earth side than the backside.
Can I follow up? I mean, maybe I got the answer, but I'm not sure I understand it. It seems to me as though the asteroids that would be large enough to create the Maria, I would presume that if it hit the backside of the moon, thicker backside of the moon, that nonetheless we would see very large craters there without a lot of recent cratering over that. And I don't think we see that on the backside. It seems to me as though these things were coming in.
There are smaller lava flows on the backside.
Yeah,
just not
there's
as
one
obvious.
small one, but that's not what I'm talking about. I'm saying, let's say, what did Apollo 11 land on? What Maria was that?
I can't remember.
Sea of Tranquility, right?
Sea of Tranquility.
Okay.
That's what it's
So
they also landed in the Highlands as well.
Okay. So an asteroid large enough to create the Sea of Tranquility, that if that hit on a highland, I would imagine that it would create a thousands of kilometer wide crater, even if it didn't get all the way through to be able to have lava flow into it, creating a Maria. It would nonetheless be a very huge crater. And then if it's a late heavy bombardment, then we wouldn't see much cratering of that afterwards. And I don't see that on the moon. I mean, maybe I'm wrong, but I don't know that I see that.
Well, it just indicates the Maria are a more recent event than what we see on the than what's left over on the backside. There's been more change on the Earth side than on the backside, since it formed.
Why was this more recent event only one-sided?
Oh, again, when the moon formed, the crust was thinner on the Earth side as on the backside. Later on, when the volcanism did occur, however it was initiated, it would have occurred much easier on the Earth side than on the backside because of the much thinner crust. And that's what we see, is that the crust is much thinner. I mean, that's what we find from the
Does anybody put
gravity
numbers
probes.
to that? Or
What? Yeah, there's
one of the things that will be interesting to see is, because Ganymede appears to be in the same general position as our moon in that regard, are there seas on Ganymede, and if so, are they facing Jupiter? Because as I understand it, all of the Jupiter's moons are locked to Jupiter.
It seems to me there are so many unknowns and so many contradictions and activities going on now that obviously went on in other places at a different time. I think we're just arguing in circles.
Well, that may be, and that's one of the things that I think when we start doing that, we need to recognize that the fact of the matter is, best thing to say is we don't know, and it's not good to be dogmatic on either side, or on any one side of a multi-sided question. Because the fact of the matter is, and until you start doing the math and you find out it will work or it won't work, you really haven't done what you need to. And I think that's, one of the things that is interesting, it comes into this argument, is how did the moon form? And the usual argument is that it was a Mars-sized body that hit the Earth, and that most of it stayed with the Earth, but some of it went off and along with some of the Earth into an object that congealed together. Now there's problems because it must have gotten beyond the Roche limit, otherwise it would have been torn apart to begin with. But there's another problem that's even more important, and that is that if you manage to get the moon up there, then one of the things I don't think that has been adequately looked at is how the moon got to the orbit it's on now. I'm aware that the theory is the Earth was spinning a lot faster, and the tides that are slowing down the Earth are kicking the moon out a little bit further each round. It has been claimed, and I don't know the derivation of the math, so I can't verify or falsify the claim, that the kicking out of the moon varies with the 7th power of the distance to the moon. Now, leaving aside challenging that assertion, which should be challenged, we should ask, is that really true? But let's supposing that it is true for now, just for the sake of argument. Then, as the Earth slows down, it imparts a certain amount of motion to the moon, which gradually spirals outward. And if you take where the moon is now and how fast it's being kicked out, and you reverse that with that 7th power, you have the moon spiraling into the Earth about 1 billion years ago, which of course is not standard theory. And the question that I have is an even more significant one, I think, and that is that if you're kicking a satellite out, it seems like the strongest kick is going to be at the perihelion, or the perigee in the case of the moon. That is, the closer it gets to the center, the more of this transferring of rotation of the Earth into the moon being further out there would be. Now, if you're doing orbital mechanics, you know that if you want to make an orbit circular, you need to fire the rockets at apogee. Because if you fire them at perigee, you simply make a more elliptical orbit. And the question I have is, has anybody done the math? Can it be done for whether the moon's orbit would be expected to be more and more elliptical as time goes on? As it gets closer to the Earth, it keeps getting that kick at perigee, but not at apogee.
The tidal forces circularize orbits and create this, cause the moons nearby to be tidally locked. So that's why we see the same face of the moon towards the Earth all the time.
Yeah, well, the tidal locking is understandable.
Yeah, and
The question that I have is why is it simply a matter that the moon is at apogee longer, and so therefore, even though it's more intense when you're getting close, it doesn't stay there for long enough, and that's why it circularizes the orbit?
Yeah, it's the differential forces that it experiences. It makes them non-symmetric. It makes them non-symmetric towards the center of the Earth, and this causes the orbits to become circularized if it's initially elliptical. Now, in terms of the motion of the moon outwards, we know that it's moving away slowly from the Earth, but
we can measure that now.
But there's no reason to believe that you mentioned the rate is related to the 7th power of the mass. I'm not familiar with that, but that's
the distance, not the mass.
The which? The distance.
The distance.
Yeah. Well, that assumes a solid planet. Now, what they're finding is that, and work has been done on this, is that there's microgravity effects that are very complex because of the Earth is not a uniform sphere that causes that rate of motion away from the away to be non-uniform. And so to say what it is now and project that that's the way it has always been is just not right. And it can be, and there's enough variation in the gravitational pull of the Earth because of its non-uniformity of its surface, of its crust, that it can that the variations that motion is non-uniform, and you can't just speculate on a specific rate. So
I would be interested in seeing the mathematical basis behind those arguments.
Yeah,
I mean, we fault Faulkner for not looking at how much nitrogen you're putting out, and I think rightly so. But what that means is that our arguments have to be every bit as watertight as we expected his to be.
Yeah, well, I know there's been microgravity experiments that have measured those kind of variations that have been applied to the motion of the moon. So,
could you hunt some of those down?
Well, I can put it on my list.
No, I'm serious because I'd like to know. I don't want to be, this kind of fits and that kind of fits. We need to put numbers behind this. How high does water ice have to be before it starts to get soft enough to where it slides past itself like glaciers do? Is that something that only happens within, effectively within, let's say, 20 degrees of freezing? Or so if we can just keep the water ice cold enough, even though we're boiling off the nitrogen, the water ice will still hold into those mountains. I mean, I think he's raising a legitimate question. I think he hasn't put numbers behind it himself, but I think that we need to start putting numbers behind it to ask, what kind of models would be adequate to
You showed
explain.
that predicted picture of Pluto, and how off it was compared to what we actually saw, because they expect a lot of craters based.
Yeah, I mean, you saw the photo of the artist drawing.
Yeah, but there are artists that have taken the science seriously when drawing those pictures. Obviously, this person hadn't for that one. There's a picture that was done by an artist for Astronomy magazine that was amazingly close to how Pluto appeared in the imagery in terms of the large-scale features.
Now, it would be interesting to know what the artist's thought process was,
well, he took into account we knew beforehand that Pluto had a tenuous nitrogen atmosphere, and so that, along with knowing the temperatures that are expected, knowing that it's an icy planet, what kind of density it had. He took those things into account in talking to the scientists about what to expect Pluto to look like, and he drew a picture that turned out to be amazingly realistic to what we actually see.
Could you bring that in with references? I'm serious. We'd like to see those kinds of things.
Well, I saw an artist's conception this morning. It didn't look anything like it.
Well, apparently there are some artists who are better than others, is what I'm being told, and it would be very interesting to see those artists and to hear what their rationale for.
He might have just got lucky, for all I know.
And that's true.
I thought it was going to look something like the moon.
But there are, what you showed was an extreme case in the opposite direction. There are artist conceptions that are much better when people.
Well, to be fair to the artist that I showed, he got the International Astronomical Union to put him up as their.
That was a publicist that put that up.
Well, obviously there weren't enough people looking and saying, that's not really what it would look like.
So scientists leave Some things up to
So
publicists.
it sounds like the scientists have as much trouble as the artists in figuring out what's going on.
Yeah.
Peer-reviewed art, somehow that...
Yeah, that's...
Anyway,
okay, thank you.
next week we'll be talking about Earth-like planets.
Planet Earth, hundreds of millions of years in the future. Intergalactic explorers return to their home planet in search of signs of ancient civilizations. They find a planet that has changed beyond recognition. Gone are the familiar continents that we know today. Instead, they find a giant landmass with huge mountain ranges, massive frozen snowfields, and glaciers. The once thriving metropolis they seek has disappeared. A few broken remnants are all that remain, crushed and buried beneath tons of rock. Could this be a future vision of Earth? Naked science asks, what forces could create such a bleak and barren world? And investigates how the awesome power of colliding continents shapes and reshapes our planet in an endless cycle of construction and destruction. Our world, the Earth. From space, it's easy to see the distinctive pattern of land that makes up the continents: North America, South America, Africa, Antarctica, Europe, Asia, and Australia. Giant landmasses separated by oceans that stabilize the environment with hospitable weather patterns, suitable for civilization and cities to evolve and prosper. Now imagine our planet ravaged by storm force winds, subjected to extremes of temperature, giant freezes, heat waves, and droughts. A world where cities are crushed and destroyed, where Africa tramples New York underfoot, and London freezes at the North Pole.
The geological future of New York is going to be rather traumatic. North America and Europe are going to collide with one another.
The world as we know it will be unrecognizable. This is not a portrait of the Earth after a devastating global disaster. This is how nature will shape our planet many millions of years in the future. This incredible remodeling is just part of a natural cycle that has shaped the Earth for the last 4 billion years, and will continue to do so until the sun finally destroys its surface once and for all. Today, our continents may seem solid, safe, and forever fixed in place, but they are none of those things. These great landmasses are constantly on the move. Speed up the last few billion years, and one can see the continents sailing across the globe. Powerful forces deep within the planet rip the continents apart and then smash them together in an ever-changing cycle of death and rebirth. Oceans disappear, mountains crumble, and rise again. Landmasses form and reform. Colliding continents are the mightiest force on Earth.
When we look at the history of planet Earth, we see that it is full of change. Change is part of nature, and this change continues today and will continue into the future.
To understand how the continents shape our world, we must first travel back in time to the very birth of the Earth. 4.5 billion years ago, the Earth is created from the debris left over from the formation of the Sun. Dust and debris collide and clump together. Once these clumps grow into objects, about half a mile in diameter, they create enough gravity to attract more material. Slowly, these clumps grow into as many as 20 planets. As these new planets orbit the Sun, they begin to collide. One collision with the planet Theia, which creates the Moon, obliterates the surface of the Earth. The energy from the collision makes the Earth incredibly hot. At around 11,000 degrees Fahrenheit, it's more than 7 times hotter than the inside of a cremation furnace. Earth is a massive molten ball of boiling lava. This is primeval hell, where thousands of asteroids and comets bombard our world. But deep within the planet, a process starts that will lead to the first land. The heaviest elements, lead and nickel, sink down toward the center of the Earth to form a molten core. The lighter elements, including oxygen and silicon, rise toward the surface, where they erupt in volcanoes of molten rock. Slowly, the Earth's surface cools. Molten lava solidifies to form patches of crust, the seeds of the first continents. But even as the first land is born, it faces a battle to survive.
We were being bombarded by a large number of asteroids very early in the history of the planet. So there's a lot of dynamic change from being walloped by giant impacts, disturbing things.
Geology professor Sam Bowring is an expert in early Earth and the genesis of the continents.
When we had an early crust is an interesting question. I suspect we had an early crust from day one. The question is, how long was that preserved? When the Earth was being bombarded constantly by asteroids, the chance of preserving any small chunk of that crust was very low.
The relentless bombardment destroys the new planet's crust almost as soon as it forms. This recycling of the surface continues for many millions of years.
But as the flux of asteroids began to wane, and as the Earth matured a little bit, I suspect the early crust lasted a little bit longer.
Eventually, the barrage from asteroid impact slows